Nice to see you all and welcome to the Monday seminar. Really happy that we're able to do it again this week. We have Chiara Cornelio, who's going to talk to us from INGV about some really interesting things she's doing experimentally and also thinking about constitutive laws for fault weakening. We have a few more seminars this semester before we'll break for the summer. We're off next week. But then we have another couple seminars in May. So, yeah, Chiara, go ahead and share your screen. Looks like there are many familiar faces and names here, so I assume you've all been here before. If you're new to this seminar series, welcome. And our normal mode of operation is to just ask you to mute. And if you have a point of clarification or something you'd like to make along the way, that's usually fine. But we have a nice extended discussion and question and answer period at the end. So substantial questions and discussion, please keep it to the end. But I think Chiara's fine to be interrupted along the way, and probably also nice for her to be reminded that there really is an audience out there and she's not just staring at her screen talking to us. So yeah, if you have some point of clarification along the way, please do that. Chiara, thank you very much for joining us. I'll turn it over to you.
Thank you, Chris, for the invitation and for the presentation. And good afternoon to everybody, and thanks to be here. So today I will show you some of our results about the constitutive behavior that we can derive from laboratory experiments and how we can use them on rupture dynamic modeling. I would like to thank all the co-authors of the works that I will present today. So I would like to start with a classical picture of the seismic cycle in which we have the evolution of the shear stress versus time. And we know that the seismic cycle can be divided in 4 parts. The interseismic and preseismic phase that can last for years. And then there is the coseismic phase that actually can last few seconds, in which the shear stress increase from the yield or initial value up to the peak value. And then there is this abrupt decrease of the shear stress from the peak value to the minimum. And these are happens in few seconds. And then there is a recovery of the shear stress to its final value before the start of the post-seismic phase. So today we will mainly focus on the coseismic phase of the seismic cycle. So when the dynamic weakening occurs and the slip on a fault basically happen. So what we know is that during this dynamic weakening, the response of the material can be described by using a constitutive law that can be schematized here with this sketch that we have at the bottom, where the shear stress evolves with the slip. And moreover, during we knew that that dynamic weakening is occurring because we have evidence from the field. So if we look at rocks that are silicate rich, we can have the formation of pseudotachylites, so the melting of the rock, and this is due to the frictional heating that is occurring during the sliding. And if you look at carbonate rich rock, we can have a mirror-like surfaces that is forming and that have this scratch that actually are the scratch that happen during the sleep, and also that thermal decomposition of the calcite, as is shown here from Colletti et al. 2013. So if you want to schematize what is happening during the rupture propagation, we can see here on the left, here there is the epicenter, then the rupture is propagating to the right. And if you look at the tip of the crack of the rupture propagation, what we can have is that if we have a silicate-rich rock, we have first the rock that is going to fragmentation, then there is the asperity melting, so the flash heating is occurring at the asperity scale, and if the slip is long enough, then we have the melting of entire patches of the fault, and in the end, the formation of entire layer of melt that is to a process that is called bulk melting. if we are talking about calcite-rich rock instead, after the flash heating, we have what is called dynamic recrystallization or viscous flow deformation creep. So during the first part of the presentation, what we can see is what the answer that we want to try to, the question that we want to try to answer is that also in the lab, we have this combination of weakening processes. And if we are able to determine the constitutive parameter that can describe these weakening processes at the laboratory scale. However, we know also that faults are not so simple, are we described by the sketch, but from a picture from the field, and these are pictures by Michele Fondres, we know that multiple slip surface can occur, but also multiple slip events can be occur on a same slip, on a same fault. So what we can see here on the right is that the grayish part is an old event, while the whitish part is the younger event that occur on the same fault. Moreover, we can identify two end members. So when the slip is occurring on a gouge layer that is here in the middle, or when it's occurring between bare surfaces. So let's say more asperity contact. And this is a way that we can also represent in the lab. So a thin principal slipping zone can be represented by two samples of bare rock, while a thick principal slipping zone can be represented by a layer of gouge. However, we are missing something that can represent a more complex behavior. So the question that we would like to answer in part 2 of the presentation is how the constitutive parameter can change between when we are just performing experiment on bare rock or respect to gouge, and if we are able to have an influence of the slip history evolution on the constitutive parameter of the material that we are investigating. So then we will also, what we can also observe is that the response of the shear stress on a point of the rupture can be described as the evolution of the shear stress versus the slip. But this evolution is actually the results of the constitutive law that we can also determine at the laboratory scale, but also of the dynamic loading. And to have the dynamic loading, we have to resolve the last dynamic equation. So in this way, we are able to study the rupture features, the feature of the rupture that's going to propagate. So in the third part of the presentation, what we will do is to study the influence of the dynamic processes and how the constitutive law that we are choosing can have an influence on the rupture features. So starting with the part 1 of the presentation, so here in this part, we are going to see the dynamic weakening occurring at the laboratory stage. And we know from microstructure that actually multiple weakening mechanisms are occurring also at the laboratory scale. For example, here on the left, we can see that, first of all, we have the formation of small patches of melt. So this means that we have flash heating at the asperity scale. But if the slip is long enough, then we have the formation of a complete layer of melt that is represented here, or if we are performing experiment on silicate-rich rock. However, if we are performing experiment on calcite-rich rock, we have the formation of nanoparticle, and we can observe a diffusion creep. So in order, so what we decided to do is to took almost 100 experiments performed on Shiva using 4 different lithologies that are gabbro, granite, basalt, and Carrara marble. We took just the classical experiment performed on a rotary shear apparatus in which we impose the evolution of the velocity as a trapezoidal function, and we record the evolution of the shear stress. So first of all, how is done, how Shiva looks like. We have a sketch here on the upper part of the slide. And basically here we have these samples, and we are talking about just a bare surface sample in this case. The rotational sample is connected to the motor thanks to this axe. While the stationary sample is connected to the axial piston that basically impose the normal stress on our discontinuity, that is our experimental fault in this case. The experiment that we choose have a range of normal stress between 5 and 40 MPa, and the maximum imposed zip velocity of 0.1 from 0.1 to 6.5 meter per second. So we are always talking about co-seismic slip rates. And what we decided to do is to try to build a model in which two different dynamic weakening mechanisms can occur. So we have first the formation of flash sheeting, so something that is happening at the asperity scale, and then some bulk dynamic weakening mechanism, so the formation of melting in case of silicate-rich rock, or the formation of nanoparticle and diffusion creep in case of calcite-rich rock. So each of these weakening mechanisms can be described using a law here. And what we would like to do is to invert our experimental shear stress in order to find some parameters that are going to characterize our dynamic weakening mechanism. And to do that, we use an optimization procedure in which we are going to minimize the difference between the measured shear stress and the shear stress predicted by the models. So to go into detail about the optimization procedure, what we have done was actually to run two optimization procedure. The first one in which we had to have the guess value for our parameters. And in this case, we are just considering one single weakening mechanism, and a second run of the optimization in which we consider the combination of two weakening parameters, in particular flash sheeting and bulk melting for silicate-rich rock, and flash sheeting and diffusion creep in case of calcite-rich rock. During this second run of optimization, what we can obtain is a distance that we call the slip switch distance, in which basically what is happening at the bulk starts to be more important of what is happening at the asperity scale. So visually, we can have here how the optimization looks like. Basically, our experimental data are represented in blue. Here, two examples: one for the Gabbro on the left and one for the basal on the right. So if we consider just the flash sheeting, we have this yellow curve over here, and if we consider just the bulk melting, we have the orange curve over here. But if we consider the composite model, we have the red curve over here, and we can identify this slip switch distance. From the experimental data, what we can see is that actually the transition between what is happening at the asperity scale and what is happening at this bulk scale is much smoother compared to what our model can predict. But this slip switch distance can give us an idea of how much is important what is happening at the asperity. In fact, what we can see is that just considering the flash sheeting model, we can represent the huge part of the stress drop that is occurring during our dynamic weakening. This happened because the decay of the shear stress versus the slip is non-linear, is more like an exponential curve. Moreover, the slip switch distance is also smaller compared to the slip. We can go a step further in our analysis, and we can analyze how the slip switch distance is changing as a function of the normal stress of the experiment, that we can correlate to an hypothetical depth of our hypothetical earthquake. And what we can see is that the slip switch distance is decreasing with increasing of the normal stress, so the depth, and the differences between the lithologies are also decreasing with increasing the normal stress. Another way to look at this graph is to look at the power density. So the product of the shear stress and the slip rate that we impose at the moment of the switch. So, and if we take, for example, a constant power density, like for example, I don't know, 20 megawatt per meter square, what we can see is that the slip switch distance is actually really changing with the lithology that we are investigating. However, for a bigger power density, this change is actually decreasing. So to summarize this first part, what we have done in this work was to study two different weakening mechanisms, one that is occurring at the asperity scale and the second one that is occurring at the bar scale. We try to combine these two weakening mechanisms using a composite model, and we identify a kind of distance in which what is happening at the asperity scale start to be less important of what is happening at the bar scale. And what we saw is that this distance is actually a function of the normal stress and so if you want of the depth and of the lithology that we are using. But all the experiments that I presented in the first part were only performed under using the bare rock samples. And on the second part, instead, we are going to look at the differences between what is happening at the gouge, if you are using a gouge sample or a bare rock sample. So already in 2015, Smith observed that there is, by imposing the same slip rate between samples in gouge, that is this red curve over here, or in bare rock, we can have a difference on the initial phase of the deformation. In particular, he identified a distance before the initial of the dynamic weakening that is much bigger in case of gouge compared to what is happening bare surface. So in this case, for example, what we can see is that this distance is actually 0.001, so 1 millimeter for the bare rock, and is 0.1 meter in case of gouge. So in his paper, he proposed this constitutive behavior for the gouge, in which we have a strengthening phase at the beginning between the yield stress and the peak stress before to reach the dynamic weakening. So we decided to study a little bit how this strengthening phase is changing in gouge material if we perform multiple slip events. So to do that, what we have done is always using the rotary shear apparatus that is installed here in Rome, so in INGV in Rome, so Shiva. And we perform an experiment on bare rock, and in this case, we are only talking about calcite material, and using gouge. So in this case, the gouge layer should be here between these two Teflon rings. And we performed the experiment under only humidity condition, imposing 3 different normal stresses, 10, 20, and 30 MPa. And the initial layer of the gouge, which we tested 2 different gouge layers, so 3 grams and 5 grams that correspond to more or less 3 millimeter and 4.5 millimeter of thickness of the gouge layer. Going to the experimental procedure, also in this case, we just impose some trapezoidal function of the slip rate, and we recorded the evolution of the shear stress. But the procedure was a little bit different between the bare surface and the gouge. In case of bare surface, we just imposed 1 single slip event. That is the green curve here. In case of gouge, instead, we performed 4 slip events on the same sample with an holding time between the slip events of 120 seconds. So For each of our sleep events, we can identify 5 parameters. That is the yield friction coefficient here, so the end of the initial elastic phase deformation. Then we reach the peak friction coefficient with a sleep distance that we call dA. And then we have the starting of the dynamic weakening until we reach the steady state friction coefficient in a distance that is called dC. So if you're going to look at how these 5 parameters evolve with the number of events and if they are different of between bedrock and gouge, we have something that is, we have this graph over here. So now we are looking just at the yield stress here, and what we can see is that this is not changing with the number of pulses. So in red are the results for 3 grams, in blue the results for the results for 5 grams, and the symbols are the different normal stress that we impose. So the yield friction is not changing with the number of pulses, and is basically similar to the bare surface result, while the peak friction is increasing with the number of pulses and is higher in gouge compared to the bedrock. Looking at the steady state friction, again, this seems to be quite constant with the number of the pulses that we impose, and higher in gouge compared to rock. And the DC distance is decreasing, strongly decreasing between the first and the second pulse, and then is more or less constant, maybe just slightly increasing during the third and the fourth pulse, and is lower for these 3 pulses in gouge compared to the bedrock. So another way to combine this parameter and is to compute what we call the normalized strength excess, so the difference between the peak and the yield stress normalized by the normal stress, in order to compare the experiment that have been performed under different normal stress. And we plot this value versus the 2 critical distance that we identify, so the DC distance and the dA distance. And in both cases, what we can observe is that the NS value is increasing with the decreasing of the critical distance. And moreover, looking at the color bar, what we can see is that also dA is decreasing with increasing the number of pulses. So the lighter color are over here, while the darker color are up here. So we can again combine a little bit more this parameter and looking what is happening at the energy. So we define the breakdown energy as the integral of the shear stress with the slip, and looking at what is occurring upper the minimum, so the steady state value. And looking at the breakdown energy, what we can see is that for the first pulse is much bigger compared to the second, third, the fourth one, and also compared to the bedrock. So to better understand where this difference between the first and the second pulse is coming from, we divided the energy in what is happening before to reach the peak, so between 0 and the dA distance, and what is happening just during the dynamic weakening stage. So here, the green area over here. And what we see is that actually the energy that is the energy before the peak is much bigger on the first pulse, and then it becomes basically 0 in the others, and it's similar to the bedrock. While for the breakdown energy during the contribution, just during the dynamic weakening, what we can see is that just slightly decreasing with the number of pulses, and for the third and the fourth pulses, it's actually really similar between the gouge material and the bedrock. So looking at the microstructure, we can also find an explanation of why this is happening. So why, energetically speaking, this material at the end of the third and fourth pulse are similar to the bedrock. In fact, if we look at the microstructure, we identify here on the upper part the principal sleeping zone. Then there is the sintered domain, so the material that have been cooked due to the increase of temperature during the shearing. Then there is the comminution domain, and then there is what we call the spectator domain. So basically a material that is really similar to what we had at the beginning of our experiment. And by increasing the number of pulses, we have that our macrostructure become more and more complex, and we arrive at the fourth pulse, in which we have two principal sleeping zones, one here, an old one here, and the new one here, in which we can also see product of the thermal decomposition. And then we can also see that all the layer of gouge is basically or sintered or comminuted, that we don't have anymore any kind of spectator domain, so initial material. Basically, we can summarize this microstructure by saying that what we started to be a gouge material, and that at the end of the first pulse, something that is much more similar to a bedrock. So to summarize what we saw in this second part of our of this presentation, what we've done was to study the evolution of the gouge and the parameter that can describe the behavior of the gouge due to multiple sleep events. And what we see is that basically the yield friction coefficient, the steady state, are basically constant no matter the number of pulses, but the peak friction coefficient is increasing while the DC distance is decreasing. Moreover, there is a huge change between the energy between the first and the second pulse, and this is due to what is happening at what is happening basically at the beginning of our deformation stage, so between the zero sleep and the DA sleep. Most of the changes occurring between the first and the second parts. And from a microstructural point of view, we have that the formation of, due to multiple sleep events, we have the formation of multiple principal sleeping zones, and then evolution of the gouge material in something that is more similar to a bedrock. So once we study, I will say in detail what is happening during the dynamic quickening and how the gouge and the bedrock can be different or not, what we like to do on the third part of the presentation is try to upscale our experimental results to study some rupture dynamics using some models. This is an ongoing work, and we have just done a few steps on this direction. And to do that, we just focus on two main features that we observe in the lab. So the presence of the existence of this DA distance, so the sleep between the yield stress and the peak stress, and it was observed not only on the experiment that we performed on Shiva, but also experiments that were performed at low velocity using large sample and small sample. And also, we want to capture this decay of the shear stress during the dynamic quickening that is actually nonlinear. These two features are not captured by a theoretical model, the linear sleep quickening model, that is the most used constitutive law for rupture dynamic in rupture dynamic models. But already at the end of the 90s, beginning of 2000, Onaka already developed a constitutive law that takes into account these features based on his experimental results. So he defined the constitutive law in which we have a nonlinear increase of the shear stress between the yield and the peak, and a nonlinear decrease of the shear stress between the peak and the steady state. So to look at how these two features can have an influence on the rupture propagation, first of all, what we had done was to calibrate the Onaka friction law using, again, the database that we have on Shiva. This time we used 160 experiments. Most of them, so almost 100, were performed on Carrara marble and 59 on Gabbro. We choose experiments that again have a cosismic sleep rate between 0.1 and 6.5 meter, range in normal stress between 5 and 40 MPa. And we also analyze experiments that were performed under different experimental conditions in terms of presence or not of fluids. so under humidity or pressurized fluids or under vacuum. And what we saw is that by just studying Carrara marble and gabbro, we can have a really difference in the ratio between dA and dC. So the dA over dC is much smaller for Carrara marble, 0.015 more or less, and bigger in gabbro, 0.08. So then we decided to implement the Honaka friction law on a rupture dynamic code that is called Rufina. The code was initially developed by Stefan Nielsen and Shane Murphy. And then together, what we have done was to implement different constitutive laws and to benchmark the code using the TPV 105 of the SCEC. So in this code, what we have done, the code is a 2D code in which we have a simple geometry, which we have our fault here that is represented in green. We impose on the fault a normal stress of 100 MPa, an yield stress of 45 MPa, an initial stress of 43. We also have to impose the nucleation that is happening here on this patch in the middle. The patch is 1.5 kilometer large, and we impose an increase of the shear stress of 24 MPa in 1 second. So to try to compare the Honaka friction law and the linear slip weakening one, we have to decide which parameter we want to keep constant. So first of all, we impose the Honaka friction to the Honaka friction law the parameter that we derive from the lab, from our 106 experiment performed in Shiva. So a dA over dC of 0.15 for calcite and a dA over dC of 0.08 for gabbro. And then we compare with the linear slip weakening one by taking constant or the DC distance, here 0.8 meter, or the energy, so the integral of the breakdown energy, so the integral of the shear stress over the slip above the minimum value. So it's the yellow area over here, or the weakening rate, so the rate in which the dynamic weakening is occurring. This is also the color code in which I will present the results in few slides. This has been done both for calcite and gabbro. And we focused on 3 main features of the rupture propagation. First of all, we look at the effects on the rupture velocity. What we can see is that if we take constants, the DC distance between the Honaka friction law and the linear slip weakening one, we are underestimating the rupture velocity. So here the purple points are lower compared to the orange one or also to the blue one. If we take the same weakening rate, we are overestimating the rupture velocity. However, if we consider the same energy, we are more or less able to have the same rupture velocity for both the Honaka friction law and the linear slip weakening one. If you look instead at the slip rate function, this is the evolution of the slip rate function with the distance from the nucleation patch. What we can see, first of all, is by comparing calcite and gabbro, is that the peak of the slip rate is actually higher in case of calcite compared to gabbro. But especially for gabbro, we have also the shape is different because we have this long acceleration phase at the beginning before to reach the peak of the shear stress. So if we look at what is happening, for example, at 7.5 kilometers from the nucleation point, and we compare the slip rate function that between the Honaka friction law and the linear slip weakening ones, what we can see again here, but better to look at here on Gabbro. We have only this long acceleration phase, so the presence of DA is producing this long acceleration phase that we don't have in case of linear slip weakening law. Moreover, however, actually, the peak of the slip rate seems to be really similar, again, if we are considering the same energy between the Onaka friction law and the linear slip weakening one. Finally, looking at the cohesive zone size instead, in neither of the cases, so no matter which one of the parameters that we decided to keep constant between the Onaka friction law and the linear slip weakening one, we are not able to catch the proper cohesive zone size between the models. Especially in the case of Gabbro, in which the ratio dA over dC is bigger. So to conclude also this third part, what we have done was to use rotary shear experiment, the database of Shiva, so rotary shear experiment, to calibrate the Onaka friction law that basically catch the presence of a dA distance and the nonlinearity of the decay during the dynamic weakening. We compare the Onaka friction law with the linear slip weakening one by taking constant or the DC or the energy or the weakening rate. And what we see is that some feature can be kept the same if we have the same energy, like for example, the velocity, the rupture velocity and the maximum slip rate. However, neither the shape of the slip rate and neither the size of the cohesive zone is similar between the Onaka friction law and the linear slip weakening one. So as a general conclusion for this presentation, what we have done, what we have seen is that multiple weakening mechanisms are involved during the weakening stage. That basically all of them impose a nonlinear decay of the shear stress. That we identify a distance of switch between what is happening at the asperity scale and what is happening at the bulk scale of our experiment. We also underline the importance of the dA distance during the experiment, so between what is happening between the yield stress and the peak stress. We saw that the dA distance evolves with the slip history of the material, especially in the case of gouge material. And finally, we try to take into account these two features, so the nonlinearity of the constitutive law and the existence of dA on rupture dynamic models, and looking at how three of the main features of rupture propagation change due to these parameters. As I say at the beginning of the third part, we are just starting to understand a little bit better how the constitutive law can have an influence on rupture dynamics. And what we would like to do more in detail is to implement also constitutive parameters that take into constitutive laws into account the evolution of the parameters due to the slip history. We will also like to implement constitutive laws that take into account what we see in the experiment as the evolution of as the increase of the temperature during the sliding, the strain localization, or for example, chemical reaction that can happen during dynamic weakening. And also can be nice to look at how the presence or not of a damage zone around an hypothetical fault can have an influence on rupture propagation. And with this, I thank you for your attention.
Thank you very much, Chiara. Really nice talk. I'll invite people to unmute and join me in thanking Chiara for, beautiful data. Really nice presentation. Thank you. Yeah, well, we let Chiara catch her breath for a second. Normal mode of operation that works quite well is to use the reaction button at the bottom of your screen and raise your hand like that. And that will put us in some sort of order to have discussion and ask some questions. And while other people are still gathering their thoughts, I'll throw out just a general comment. Really beautiful data, Chiara, very nicely explained. So thank you very much.
Thank you.
Can you say a little bit, like, so your weakening distances, I guess that was covered kind of mostly in the first part of the talk. Thermal weakening distances were often about 1 meter or so. In some cases smaller for higher normal stresses. So then, does that set a minimum size? Do you think of it? Does that set up a minimum size for this kind of earthquake? Because, okay, sure, for big earthquakes, there's no problem accumulating 1 meter. But what about I don't know, what about a magnitude, 1 or 0.5 earthquake? Does it slip enough to really weaken, or does it just behave in a different way, do you think?
I think just looking at the data that probably for a smaller earthquake, we don't have a complete decay. So we don't reach, in case, for example, of Gabbro, complete bulk melting of our material. But maybe we stopped before. But since the weakening is actually non-linear, it just with few centimeter of slip, we can have a huge decay of the shear stress, or if you want, the apparent friction coefficient in this case, due to weakening, to thermal activated weakening processes. So maybe it's actually, this is bigger because the decay is non-linear. But if you want to consider just only, I don't know, 60% or 80% of the decay, we need a smaller distance that can represent this loss of strength of the fault.
I see. Yeah. And I guess it depends also on your gouge thickness and on the zone over the thickness of the width of the zone that's shearing, how much material is in it, things like that.
Yeah.
Yeah. Thank you very much. Cristiano, go ahead.
Ciao, Chiara, and thanks a lot for your nice presentation. In your first part of the talk, you were proposing a switch in weakening from the asperity scale to the bulk scale. Can you better define the meaning of the bulk scale? How wide is this zone influencing the weakening mechanism?
Yeah, what I mean here for bulk scale is if all the surface of our sample is, for example, covered by bulk melting. So not just something that is happening at the asperity, so stress that is concentrating in the asperity, but what is covering all the sample. I cannot define actually width, for example, for bulk melting. Because the experiment that we are looking, the results that we are looking here have no vessel, so we are losing it. So I don't know if I can really think about a thickness.
Anyway, it is always
case.
something that is mostly concentrated along the principal sleeping surface. It's not something that is expanding away.
No. In fact, also from the optimization procedure, the thickness that we are considering is always around 200 microns. Yeah, 200, kind of 100 microns, 200 microns, for example, for a viscous creep. And actually, this is just a first attempt of optimization. So we kept constant this thickness. We are not let it increase with the sleep.
Okay, and as we go to John Rudnicki's question, I would really like to encourage everyone to raise your hand, get involved in the discussion, questions or comments. John Rudnicki, go ahead, please.
Yeah, really beautiful data, and I like your interpretation of it. I have a suggestion that might be useless because I have no idea how to implement it, but you have this history dependence and you have multiple mechanisms. And it might be useful to think about describing that in terms of state variables. So similar to the friction one, but you have multiple mechanisms, so you're going to need more. But, you know, Andy Ruina and Jim Rice have shown how the state variable in friction can be interpreted as a integral over past history, which is really what you're interested in. So yeah, as I said, I don't really know how to implement that at all, but it might be worth giving that a little thought in terms of the kinds of things you're observing.
Yeah, thank you for the suggestion. I know that there are some already some written state friction law that take into account, for example, the change in normal stress or the change in temperature. I really would like to try to understand if we can implement also this change in some of the feature that we observe in the lab.
Yeah, in the
Yes.
first part of your talk, you had the transition from
Also, yeah,
flash heating to bulk melting. And
yeah,
yeah, I mean, when I heard that, I think about, well, you have two mechanisms that are going on at different rates. And
yeah.
so, yeah, that might just be a useful way to think about it. So yeah, really great presentation. I really enjoyed it and learned a lot.
Thank you. But in this case, both of them are linked with temperature that is evolving at the slip surface, both of these two mechanisms. So I think that maybe a way to try to implement them is to try to take into account of the temperature that is evolving during the shearing, maybe.
Yeah, I think that would be necessary.
Yeah.
Yeah, it's a really interesting point, John and Chiara, because, right, so the heat, you're generating heat, but of course you're always also losing heat, so that your state variable would have to somehow, you know, bring both of those things together. And it makes me even, ask here, Chiara, in the model, what do you assume about the thickness of the zone that the heat is being pushed into? So the temperature goes up, it's always 200 microns thick? Is that what you said?
Here in this composite model, no, all the sample is involved in this case.
Oh, I see.
So in the model, I impose a constant temperature of the room temperature on the far away from the sleeping surface, and then there is the diffusion of the heat that is produced during the shearing, so the sample kind of warm up a bit, but it's for sure is much more localized on closer to the slip zone compared to the rest of the sample.
Oh, I see, but the model just assumes that that heat is
Diffusing.
evenly. I
Is
see.
diffusing, yes. So especially for the bulk model, the bulk melting over here, we are solving a Stefan problem. So we have the boundary, so is a little bit moving as a function that we reach or not the melting temperature of the material.
I see. Yeah, okay.
Yeah.
Yeah. Please, other people, join the discussion. Massimo Coco, go ahead.
No, if there are nobody else that want to make a question to Chiara, I want to make two comments. The first comment is to respond to John, because actually, John, when we use the rate state friction in dynamic models with a single state variable, like the sleep law or the aging law, it was a surprise to receive as a feedback the sleep weakening law. And more important, it was a surprise that the residual stress remained constant. So your question could be also further implemented to say, if to take into account of the real processes, we add a second or further state variables, which would be the effect of the weakening rate and residual stress. And I would bet that the effect would be that the residual stress is not constant anymore. But also with a single degree of freedom, actually, there is a slight change with the sleep weakening law because the heel stress is different from the peak stress. But the slip, what Chiara called DA and Onaka called DA, is extremely small, so almost negligible. So it is clear that if we use rate state, the question is how much can we model with the state variable our ignorance, to put our ignorance into the dynamic system. So I think that your point is good, but to me, it's still something to be better understood, while a single degree of freedom provides a slip weakening law.
No, I agree with you, but I had in mind that you're going to need to go beyond a single state variable and one that represents the different mechanisms that come. But yeah, it sounds like you have a much better idea of how this might be implemented than I am. So yeah, I agree with you, really.
Yeah. And the second general comment that came out from the work that Chiara is doing is that we need to keep the benefits of using the linear slip weakening law, because it has been a fundamental progress in earthquake mechanics. But in my opinion, we need to start thinking a bit broader, because the linear slip weakening law has a lot of limitations and restrictions. And therefore, our interpretation are really focused on this. And that was Onaka was suggesting, even if Onaka was convinced that the sleep is the state variable, is the constitutive variable, and this might not be the case.
Chiara, thank you for coming to this slide, and chime in. You're in charge.
No, I come to the slide to underline the difference between what we observe in the lab and what actually in the linear slip weakening model is taking into account. So for sure, this DA I think is quite important. I'm not sure that the sleep is the key parameters to understand everything. But this is a kind of simple law in this case, and the comparison between the Onaka and the linear slip weakening was, I think, the first step to better understand if what we obtain in the lab can be upscaled using rupture dynamic models.
Mhm. Yeah, it's interesting. It's called a simple model. It's got a lot of parameters in it, but you know, in the end,
In the end, the main parameter is this ratio over here.
right, and it just gives you a weakening to some level. It doesn't really
Yeah,
talk
exactly.
about that
Yeah.
level. Yeah, and so, yeah, one of the points I think that, you know, John and Massimo are bringing up is just, what else can you do to make it really weaken? You've talked about temperature, that works, but yeah, rated state, because the strength is simply a function of friction, is simply a function of the log of velocity, then you're not going to get a ton of weakening out of it, because after you implement the first few parts, you've got to go, you know.
Yeah, actually, the modelers now I would say dynamic models, start to implement something that is called enhanced velocity weakening. So that is where the shear stress is evolving with the logarithmic of velocity for low velocity, and then with the inverse of the velocity for higher velocity. However, I think that this law that can be really useful. We are missing the parameters to put on the law. So most of them are just assumed without any experimental constraint. So I don't know.
Yeah. Other comments? While people are thinking, another comment asked, another point that came up listening to Chiara's really interesting talk in nice data is, you know, in earthquake faults, sometimes when there's a dynamic rupture, there's brecciation. Does anything like that ever happen in your experiments? Do you see a recycling of the shear structure in your fault, or does it always just continue to be more and more localized?
I'm just thinking, if you look here at this microstructure, what we see here there is the formation of two principal sleeping zones. However, if we increase, for example, for the third pulse, again, we can recognize only one principal sleeping zone, and then a second one occur again at the fourth one. So I think that at least in our experiment, we are reprinting the principal sleeping zone. So we are not able to see exactly what is happening during the dynamic stage, but we have a picture just at the end. For sure, what we know is that at the end of for the material, I don't know why, but probably because it was cooked, was easier to move from an energetically point of view. So to keep constant the energy was easier to move the principal sleeping zone far away from the old one and then not reactivate the same, because then the energy it's basically constant.
Mhm. Yeah, it's interesting. Your pulses were always done with the same time, the waiting time between them?
Yeah.
120? Yeah.
We choose 120 seconds to have enough time to cool at least the principal sleeping zone. We didn't try to perform experiment with different holding time to see if these have an effect as well on our results.
Mhm. Yeah, interesting. Thank you. Well, all right, Chiara, it seems like you've convinced everyone. I don't see anyone else raising their hand, asking more questions. Okay, Elisa Tinti, Professor Assatinti.
Hi, Chiara, thanks for your presentation.
So,
Very nice.
thanks.
I have two questions. One concerns the idea that you test two examples because you see the two material in the experiment. So your ratio between DA and DC is 0.01 and 0.08. So 8 times larger than the first one. So have you in program to test a range between these kind of ratios to see if there are some similarities, differences, and so on? Because I imagine that these differences can be larger too or in between. So to see what happens instead of having only two examples like these two.
Yeah. We were thinking that actually looking at the data of gouge, probably the DA over DC will be bigger, especially if we don't prepare the sleeping surface, let's say. For example, looking at the data, sorry, I'm going back and forward here. The DA and the DC, this is versus time, so we cannot really look at the ratio in sleep. But I guess that in the case of gouge, DA over DC will be bigger. So probably what we can do, and probably what we will do, is to increase the ratio to see how is changing, or is the feature that I described of the rupture propagation is also changing. The reason why for now we stay on this value is because in just calcite and gabbro is because we have a larger data set for these two materials compared to the others. So it was just from experimental reason.
Yeah, because you showed us some systematic behavior. So to see more examples is more simple to have more examples.
Yeah.
And is related to the rate state that Massimo mentioned, because if you use a simple rate state, you will see a sleep weakening behavior that has in some way a DA that can change along the fault. So my question is, if you want to in some way reproduce a rate state or do something that is variable, another idea can be also, I don't know if it's possible in your code to change this ratio along the fault. So in space to see what happens. Because I imagine that the DA is reducing when you're going faster and you have more dynamic load to increase the
This can be actually a good idea also to see if we can stop the rupture somehow, if we are really increasing a lot. For example, if there is a patches of something that has a bigger DA, DA over DC. We didn't thought about for now. We stayed simple. We try to understand what's happening in a simple model, but yes, can be done, and probably is something that we have to investigate a little bit more. Thanks.
Yeah, interesting point, Lisa. Someone else has a question or comment?
Chris, can I make a comment on this Lisa question? Because to me, this is a point that also raises the question of what we consider a constitutive law, or what we consider the shear stress evolution during dynamic propagation. As Chiara has shown, the difference is that when you have a dynamic propagation, we have a further contribution, which is the dynamic interaction of neighboring points. And therefore, the question is how much dA and dA over dC affect the rupture is also a measure of how much dA and dC might change during dynamic propagation. And this is really something that is not easy to test, but it would be worth trying to investigate this. But the reason why, to me, the reason why dA make a difference is because in principle, if we assume that the crack tip position is at the tip, at the peak of the stress, therefore, in principle, when you have dA that is not negligible, the breakdown work might differ from fracture energy. Unless you follow Vonaga, in which position at the beginning of the position of the crack tip at the initial stress. But Jim Rice and Vonaga, they had a different definition of the stress evolution at the crack tip. They position the tip at different points in the stress evolution. And this is a question of interpreting if what is happening between 0 and dA, as Onaga said, is an integral part of the breakdown process, or if we associate the breakdown process only to dynamic weakening. This makes a difference between breakdown work and fracture energy, or our interpretation of fracture energy. And this, to me, is the idea why we need to start thinking a bit broader than the classic linear slip weakening law.
Chiara, I'll let you go first if you would like to chime in about this.
I don't know, because we are still trying to understand our simulation results, but yeah, for sure, there is also then also by the definition of the cohesive zone, then make these results really different. So also the rupture propagation can change. We have to think a little bit more in detail, I guess. Yeah.
Yeah, I agree. And Massimo, I think those are all good points. But I suppose for me, it's useful to distinguish between parameters in a model and descriptions of them. You say, oh, well, there's a difference between where the peak stress is in those two models. Those are all important, but they're important from the point of view of talking about a description. The physics of what happens in a fault zone, yeah, it depends on heterogeneity. It depends on what the initial stress really is and variations in it along the fault. So, you know, a bigger problem than the way to describe it, I think, is just knowing, you know, what that range of physical behaviors and systems is in different parts of the fault, like how much spatial variation there is along the fault. So, yeah, those are complicated things that Chiara's experiments have some, you know, useful things for us.